In this video, I will go over the significance, basic theory, and how to apply Fourier series. A Fourier series is a special sum of sine and cosine functions which allow us to represent any periodic function. First of all, it is an essential tool for physicists in solving partial differential equations, which are at the heart of high-level physics in fields like quantum mechanics, electrostatics, and the study of waves. Another important use of Fourier series is in signal processing, which allows complex audio, visual, and other data input to be decoded, stored, and transmitted across devices. First, I'm going to show you what a Fourier series looks like, and then we'll progressively break down what the Fourier series means. So a Fourier series basically states that a function f of x, where f of x is periodic, and that function can be represented by first a term called a sub 0, which changes the height of the function. Added to that, the sum of sine and cosine terms. And so that's denoted by this notation. A sub n cosine of nx plus b sub n sine of nx. And so this section here says that it is a weighted sum, meaning that we are summing different amounts of each cosine and sine term. So say, for example, we might be summing 1 time of cosine of x and 0 times of sine of x, and we may be summing half of cosine of 2x and 1 of sine of 2x. So that's basically what a weighted sum means. It means that you can specify how much of each sine and cosine term you want to add to your series. A Fourier series can capture the properties of any periodic function. So now I'd like to talk about these properties. So the first property is period. Number 1. And the second property is the shape. While the third period, more nuanced one, is called the phase. Before I get into the mathematical representations of these 3 properties, I'm going to first move to an example involving music. Now, the reason that I am using music as an example is because sound is a vibratory phenomenon, and naturally it travels as a wave, and a wave is periodic. But when you see sound, it doesn't look very periodic. That's because Fourier series is involved. Now, there are 3 distinct qualities of sound. Number 1 is the pitch. So that's how high or how low your voice sounds, or the note you play on an instrument. And that is the frequency of the vibration, which denotes what pitch something is. And frequency relates to period, the period of a function. The second quality might be the loudness. And the loudness is determined by the shape of the function. The third quality is timbre. And this one is basically called the tonal quality or something like that. It basically allows you to distinguish if you played one note on one instrument and played the same note on another instrument, it would allow you to distinguish between the different instruments. And that's also determined by the shape. Now, this third quality is something that you probably can't hear. It's called phase. And that is determined by where the waveform starts. As you can see, we have quite a complicated waveform here. What Fourier series does is it basically decomposes these patterns into a sum of simpler patterns that, when added together, make this complex pattern. Now, I recommend you play with this application to familiarize yourself with the concept of Fourier series. Now, this will give you a real good intuitive grasp of what Fourier series are doing. It even has sound where you can play what your waveform that you made sounds like. The link to this software will be provided in the description. You do need Java to run this. And also, this website has really good simulations that teach you about physics, chemistry, and all the good stuff. The first problem we are going to concern ourselves with is how do we make the period of the Fourier series the same as the period of the function that we want to represent. And to do that, what we want to do is make the period of our cosine and sine terms the same as the period of the function that we want to represent. And to do that, we write each sine and cosine terms as cosine of n times kx, or sine times n kx. And k is dependent on the period. Specifically, if we want a period p, then all we have to do is make k equal to 2 pi divided by p. And that's how you fix the period of your Fourier series, so it can represent the period of your periodic function. Now I'm going to do a rewrite of the Fourier series in a little bit more general form. So this one only represents functions with period 2 pi. So now I'm going to rewrite this such that it can capture functions with any arbitrary period. So here, L is half a period, and this will simplify things later. Next, how do we represent the shape of the function? Well, we are already given the shape, let's suppose that, given as f of x. And the way that we can make our Fourier series represent that f of x is that we adjust a sub 0, a sub n, and b sub n. We want to determine values for each of these with the information from f of x. And to do that, there are a few formulas which I'm going to go over later. For now, let's move on to phase. Now, phase basically refers to where the periodic function starts. So basically, that's shifting the graph left and right. And we don't really have to account for the phase because the fact is that adding sine and cosine terms counts for that phase difference, because the addition of cosine and sine terms is actually equivalent to shifting the graph left and right. Earlier, we have established that in order to represent the function, we need to capture its shape. And in order to capture its shape, we need to find each of the coefficients. And here are the results from the derivation. In a later video, I'll go over the derivation of these formulas. For now, we can use the results that we have obtained to do an example. A good way to end off our discussion here is if I go through an example with you. Now, this example will illustrate how you would go about solving a typical problem involving Fourier series, whether that's in representing a function or you're trying to solve a boundary condition problem in partial differential equations. This method is usually how you would go about solving them. So let's start. Our Fourier series was that f of x can be written as a sub 0 plus the sum from n equal to 1 to infinity of a sub n times the cosine of n pi over L x plus b sub n times the sine of n pi over L x. Now the first step, we can already solve for L. L depends on the period. So as we can see here, the period is 2 pi. So we have a period of 2 pi. I mean, not 2 pi, period of 2. So L is half a period, so L is equal to 1. And we can already plug that in to simplify our Fourier series. Now our task is to find each of the coefficients. So we have a sub 0, we have a sub n, and we have b sub n. So let's get to that now. Let's start with a sub 0. The formula for a sub 0 was equal to 1 over 2L times the integral over 1 period. So that can be from 0 to 2L of the function dx. Now L is just 1, and so this integral, we can actually evaluate it visually. It just involves f of x. And we know that f of x looks like this over the interval that we are interested in. And what we can see is that, so here we have the x-axis, and above is positive area, and below is negative area, and the positive area has dimensions of 1 by 1, and the negative area also has dimensions of 1 by 1. So they just cancel out, and we get a sub 0 is equal to 0. The next set of coefficients, a sub n and b sub n, are sequences, which means that they're a list of numbers with the index of n. And first of all, let's get to a sub n, and this one is special. I'm going to prove to you that a sub n is equal to 0 without doing any integration. How I made this conclusion is because I've considered odd and even functions. Now, an odd function, as you know, is a function where if you reflect your function about the y-axis, it's the same thing as the function before, but reflected about the x-axis. So it's the f of negative x is equal to negative f of x. While an even function, if you reflect an even function about the y-axis, it's the same as the function itself. So f of negative x is equal to f of x. Now let's consider the function we have here. So we had our f of x. Now what f of x looks like if you extended it, so that way it goes into the negative as well. So that's positive x, positive y. And f of x looks like something like this. And so you can see that if you reflected this part into this part, it's the same thing as if you flip this. So same thing as that flip. So this is an odd function. But cosine terms, cosines are even. So we cannot hope to add any even terms, or else this wouldn't be a pure odd function. So therefore, we conclude that all cosine terms are 0. You can use this fact for any function that's odd or even. If it's odd, then you can rule out all of the cosine terms. If it's even, then you can rule out all of the sine terms. We're gonna have to use the formula for b sub n. So in this case, b sub n, after substituting in L, will be just equal to the integral from 0 to 2 of f of x times sine of m pi x dx. Now you can think of b as sort of a function of n. So we have n here, but the integration is with the dummy variable of x. So we can treat m pi as a constant in our integration. So what we can do is, since f of x is piecewise, we can cut up our integral into two pieces. So one going from 0 to 1, and in that interval f of x is 1, so we are only integrating sine of m pi x dx. And then we add that to the integral from 1 to 2, and in this interval f of x is negative 1, so we just multiply it by negative 1 times sine of m pi x dx. Now after doing the integration, we should have b sub n in terms of only n. So I'm going to do that now. So now we have b sub n in terms of n. We can simplify this further by looking at this term here. So cosine of 2 pi n is equal to 1, while cosine of pi n is alternately 1 and negative 1, depending on whether n is odd or even. If it is odd, then we get negative 1. If n is even, then we get 1. So let's plug that in. So this is for even n, 1 minus 1, that's 0 for even n, I mean. And 1 minus negative 1 is 2 for odd n. So b sub n is equal to 4 over n pi for all odd n. And there we have it. We have determined b sub n. So now we can write the Fourier representation of our function. So f of x f of x is equal to the sum from n is equal to 1 to infinity of 4 over, so for odd n, we can write n like this, 2n minus 1 times pi times the sine of, again, 2n minus 1, because we only want the odd n's, times pi x. And that's our answer. I'm going to graph the result. So as you can see, I have the infinite sum written here where we can vary n. And this is what it looks like as n increases. So the number of terms that we add increases. As you can see, the more terms that we add, the better the approximation. And indeed, the shape is of a square wave and it has a period of 2 pi. Not 2 pi, 2. Now that we have covered the basics of Fourier series, we can move on to slightly more complex, slightly more advanced concepts, such as partial differential equations, how to solve them using the Fourier method, Fourier transforms, Fourier analysis when dealing with complex functions, and a generalized notion of Fourier series, where we consider many more different function types, so not just trigonometric functions. For now, this is all I'm gonna cover, and stay tuned for more. Goodbye.